Hello, my name is Wook-Keung Song. Today I'm going to talk about a new method to identify and quantify BSR events in relation to testing audio devices. This work has been carried out together with my colleague Alan Koo, but today I will be the one presenting the work. BSR noise has been a major problem for many different industries, including electroacoustics as well as the automotive industries. It certainly degrade the quality of the product. So therefore, it has been addressed to deal with as soon as the problem appears. Impulsiveness metrics are used for detecting such event. And these three researchers have actually done this before. And the idea is to make use of a hearing model to mimic how we perceive the sound. And output of the hearing model is actually post-processed to detect the impulsive events in the signal. So it's the more analytical impulses has been analyzed, as well as the how people perceive the impulsive events are considered as well. Other researches could be the second one, Klippel has suggested to use a residual distortion, which is the difference between the measured output and the desired output. And it's a quite effective way. That's what ultimate goal is actually to compare the ideal one versus the actual the signal. However, this does not take into account the perceptual aspects, for example, like a hearing threshold or the loudness. Third approach is making use of PEAQ metric, and this approach is good because PEAQ is actually designed for quantifying the audio quality. However, the output of the PEAQ is fitted with the perceptual BSR, perceptual aspect of BSR events. And that output features, among those, they have omitted to use the time varying aspect of the model. So that could be the limitation of this kind of model. In my presentation, I'm going to show that this may fail for more complicated setup. So therefore, the goal of the research has been to make a non-intrusive BSR metric based on time-varying loudness, because time-varying loudness contains the how we perceive the sound as well as the nonlinear mapping from the pressure to the loudness relationship. And we know that the loudness is the most important factor that affecting the perception of annoyance. So therefore, this also makes sense. In this context, the non-intrusive means that we don't make use of separate BSR, the separate reference signal for BSR metric. And at the same time, another goal is to validate the developed metrics for the more realistic scenarios like loudspeaker driver units, as well as more complex scenario such as multi-channel audio system. Here, I would like to give a short introduction to linear deconvolution technique. A log sine sweep can be defined in this equation over here between the frequency omega 1 and omega 2 in the period of time of t. If it is a linear sweep, then the impulse filter is simply the impulse signal itself and reversed along the time axis. However, since it's a logarithmic sweep, we need to calculate the envelope as shown in this equation, and this envelope has to be compensated for. And once this compensation is done, then we can get the impulse filter ft, and the output impulse response function, or the system impulse response function, can be calculated by convolving the output signal yt with the impulse filter ft. This kind of a sweep technique has an advantage that we can separate the linear impulse response function from the rest of the harmonic related impulse responses. And at the same time, the derived impulse response function does not suffer from time aliasing, which often be the problem of circular convolution technique. So the idea is to get the linear response, which is calculated by convolving the input signal with ht, that is derived here as an impulse response function. Use that as reference signal. To validate the idea, we made a simple setup as shown in this picture, where we have placed the microphone close to the loudspeaker unit. And in this example, we also show that the artificially created artifacts, which is the metal piece, is placed on the membrane. And in this particular example, that we have used the 3.5-inch loudspeaker driver unit, which is used to assemble the type 4227 mouse simulator. 0 dB in this case indicates the maximum excitation that does not give rise to the contact between the microphone and the loudspeaker membrane. The figure below shows the impulse response function in dB. X-axis is the sample number. So as I mentioned, the linear deconvolution has an advantage to separate the linear impulse response function and the rest of the nonlinear harmonic responses. And by showing that as a dB scale, it's clear that the compared to the linear impulse response function, which is the last impulse in this figure, the rest is actually at least 50 dB down. So the influence of the nonlinear harmonic distortion to the loudness is quite minimal. This slide shows the defects that we made to create the artificial artifacts. Two of the defects, for example, banker wrench in the upper left corner, as well as the centered mesh condition, they are the ones that are significant modifications, so that even with the lower excitation level, we could clearly hear the BSR noise. Whereas compared to them, clip condition is relatively small modification, and for clip between terminals shown in lower left corner is actually the minor change that we made, so that the lower excitation level, we couldn't really hear the BSR noise, but if we excite the driver with a higher excitation level, then we could hear a very soft BSR noise. So these conditions contain the significant ones as well as the non-significant modifications for validating our metric. As I mentioned earlier, loudness is the most important factor that of affecting perception of annoyance, and therefore making use of time varying loudness is actually a good strategy to quantify BSR event. So what we have shown here in this slide is the loudness spectrogram which is the output of the time-varying loudness calculation. In left-hand side, there are two plots shown in the linear scale. So the first plot is linear response, so there is no BSR events involved. And the second plot shows the actual recording. So we're supposed to have a BSR event in this spectrogram. So what is clear in the linear scale is that we are not able to see the VSR event. And therefore, I have transformed the plots in logarithmic scale. And what is clear to see is BSR events around the 4 second. That is clearly audible as well as visible in loudness spectrogram. Therefore, what we find out is it makes sense to make use of a logarithmic scale when making a metric to determine the BSR event. So designed metric is a simple two-norm of a difference metric, which is the difference between the calculated loudness between measured and the linear response. And the result is then transformed to dB scale. So what we are looking for is the difference where there is no excitation is present. So this black area, if there is anything happens there, then we can identify that as a BSR event. This slide shows the effect of excitation level on the calculated metric. Each figure shows the result on each different physical configuration that I explained in the previous slide. It is clear that the higher the level of excitation it gets, easier to detect the BSR event. Most of the conditions, it was quite easy to detect BSR event even at relatively low level of excitation. However, for clip between terminals, the conditions were rather challenging. In this particular example, it was only detectable when the level of excitation is -4 dB and above. And from our informal listening test, this corresponds well with with our experience. So this clearly shows the metric is able to detect the BSR event as a function of different level of excitation, and tool can actually be used to a more generalized applications. In the previous examples, we have made relatively large, significant changes to the physical setup. So it's probably not very realistic. So to make it more realistic and apply to smaller changes of physical setup, we have selected the 13 loudspeaker driver units and tested on overall SPL and TST and Raman bars. Overall SPL is basically the frequency response function. So the results are shown in the figure. As we can see, most of the loudspeakers, they seem to be quite similar. The loudspeaker 4 and 13 seems to be slightly different. However, by listening to recorded signal, we could find out that there was no perceptual difference between these two loudspeakers. So these traditional measures seem to lead to a misleading of the misleading conclusion. At the same time, listening to one of the loudspeakers, we could actually clearly hear the audible broadband burst, which was not detected by these metrics. So that was loudspeaker 3, which had very audible burst during the excitation, and to confirm that the traditional measure cannot detect this event, we have compared the average THD in our urban bursts from 13 loudspeakers with the result of speaker 3. And in terms of THD, they seem to be very similar, but Robin Voss shows that the speaker 3 is actually even lower compared to the average result. So clearly that traditional measures cannot detect this event. However, if we calculate the loudness spectrogram as shown in this plot, this audible burst is clearly visible in the spectrogram, and afterwards we calculated the loudness metric that we have proposed here and seen in the figure below. That is clearly shows that the loudspeaker 3 stands out of the from the rest of the loudspeakers. Loudspeaker 4 and 13 were mentioned in the previous slide. They don't seem to be that different, so that also corresponds well with our informal listening result. On top of this, we also made a small damage to the driver unit directly, and we also repeated the test just to see that how reliable the result is. The small slit is visible in this picture that is in the slide, and right-hand side shows the frequency response as well as THD and Robin buzz. What is clearly visible is actually a frequency response function, and THD doesn't seem to reveal the damage. However, Robin buzz metric seems to be able to distinguish the damage that we have made. Lower right corner, we have displayed the overall loudness as a function of time, which we call total loudness versus time function. That if we compare between the loudspeaker 2 and the loudspeaker 2 with the slit, there is a clearly increase in loudness with the slit. So this shows the potential on a loudness metric. This is also due to that the loudness metric is actually related to how we actually perceive the sound. So far, we have applied a proposed metric to a rather simple scenario where the delay between the excitation to the microphone is minimal, and at the same time, the no nonlinear processing is involved. However, a typical multi-channel audio system contains the nonlinear processing in DSP as well as the effect of room. So in the next few slides, I'm going to present how the proposed metric performs in comparison with the traditional quality measure such as PEAQ. A multi-channel audio system sometimes consists of a large subwoofer, which then excite the panels installed inside the car. Typically can generate rattling sound. So such a BSR event can be a cause of a decrease on this customer satisfaction. So here, since the nonlinear processing is more involved in the DSP of the multi-channel audio system, we wanted to use total loudness as a function of time rather than loudness spectrogram. Total loudness has the feature that makes smoothing of the underlying calculated loudness values, because the temporal integration function is typically a low pass filter that makes the function very smooth, and thereby underlying small changes of the delays may not matter in the calculation of the difference between the reference response and the system on the test. So the idea is first we calculate the HL and HR, which is the impulse response function to the left ear and then the right ear, then combine that with the input signal XT. Then we can get to the linear response of the left ear and the right ear signal. HT is called the binaural vehicle impulse response function. Typically is measured between the stereo input to the multi-channel audio system inside the car and then 2 ears of the head and torso simulator. The calculated linear response by head is used to calculate the total loudness of that. And then the original signal YT, which is recorded inside the cabin, is used to calculate the N YT. So difference between these two and then taking the mean value of that is actually the proposed metric in the following study. So as I mentioned, the advantage is that this N total loudness contains a little more smoothing function, and also the summation across different BARC bands that can give some advantages when there are a lot of small changes involved in the signal processing of the DSP box as well as the effect of the room. To calculate the mean loudness difference, we have used a binaural loudness model based on the 3 dB loudness summation rule. And this will then combine the left ear and right ear signal and calculate the loudness values. The left-hand side figures shows the comparison between the total loudness of the measured signal and total loudness of the linear part of the signal. So when we look at the low volume versus the higher volume increases naturally the loudness, and we can see around the 10 seconds at the higher volume that the difference between the measured and the linear response seems to increase. This may caused by the BSR events created by the system, and we can see that more clearly by subtracting these two responses, the blue and the red curves. And that is that results to the two figures in the right-hand side, where clearly shows that at certain frequency of excitation, the BSR events increases. And it's also clearly visible that the higher level of excitation give rise to higher the level of BSR signal. This seems to be quite clear on the difference, loudness difference function, and taking the mean value of this loudness difference function, hopefully we can quantify the difference between the different BSR events created by the systems. This slide compares the result from different metrics used to predict the BSR event. And when we use the PEAQ, we have used the linear response as a reference, and so as for the other loudness difference metrics that we have used in the right-hand side of the slide. When using PEAQ, it seems that there is no difference among the conditions, and these conditions include the level of excitation as well as different cars and DSP settings. So it doesn't seem to distinguish these differences. This may be due to the level of excitation being quite high, so the BSR event is sort of masked by the other changes involved in the DSP settings or of the level of excitation. So compared to that, loudness-based predictors seems to be able to distinguish the difference between the conditions. And from condition 1 to 4, we do not supposed to have any BSR events. That was confirmed by the listening test. And then from 5 to 10, 5 to 12, we would expect to have some BSR events depending on the level of excitation. Here, due to the confidentiality, we cannot show the result from our subjective listening test, but we have performed the listening test where we asked the subject to judge the BSR noise contained in the signal. And we can mention that the total loudness-based metric correlates the best with the subjective results. So therefore, this could be a good metric to predict the BSR events when the more nonlinear processing is involved in the system on the test. Summary of the conclusions so far. A non-intrusive BSR testing approach is developed. The approach does not require a separate reference measurement, so therefore it's more efficient and reliable, we believe. New BSR metrics are developed based on the difference on time-varying loudness spectrogram and the total loudness between the linear response and the measured signal. The loudness spectrogram based approach can distinguish the minimal changes, small changes involved in the process, whereas like a total loudness based approach can sort of smooth out those changes, thereby more applicable for the systems that involves small changes on different conditions. Set of artificially generated artifacts are introduced, and they could be characterized quite well with the proposed metric. And it's naturally, of course, the high level of excitation gives rise to the better and easier way of detecting the artifacts. When a multi-channel loudspeaker system is tested, it's more complex because the system on the test, it involves the nonlinear DSP processing as well as the effect of room, and therefore we have used the total loudness as a metric measure, and then the proposed metric can easily detect the changes introduced across different conditions, and it matches fairly well with the result from subjective listening test. Compared to that, traditional metric PEAQ failed to detect the changes across different conditions, and this may be due to the fact that the introduced changes are much bigger compared to BSR event created by the system. Some future works, we need a lot more samples to validate the algorithm. So we are looking for a collaboration. So if you are interested, you're welcome to contact us so we can maybe apply our algorithm to your recorded data. And possibly a machine learning algorithm can actually be used if we want to make a more complex border between different types of BSR sounds. And as an example, that one of my students made a project where we have actually made two different types of rattle sounds, as well as the sound without the rattle event, and then extracted different types of features and calculated two principal components. On the x-axis was principal component 1, y-axis was principal component 2. Then by using the dim neural network, we can distinguish these samples into 3 different categories and then mark that as different colors. So as we can see that the borderlines, that they are not simple linear function, but much more complex functions. So in such a complex task, we may need to use machine learning to improve the accuracy of the quantification that we are aiming at.